Word up, my chem peeps! What in the heck are we gonna do in this vid? We're going to describe and calculate the relationships between volume, pressure, number of moles, and temperature for an ideal gas as described by Avogadro's law, Boyle's law, Charles's law, Gay-Lussac's law, and the combined gas law. Whew, sounds like a doozy. First, we're going to explain the relationships between those variables pressure, temperature, volume, and number of moles using gas laws. And then we're going to use those gas laws to actually calculate the changes in those different variables. Now you might be saying to yourself, wait a minute. What are all these different laws about? Didn't we already talk about the relationship between pressure, volume, temperature, and number of moles? Using the ideal gas law? Using my good friend Pivnert? And you would be right, we already did. All these crazy sounding gas laws are just variations of the ideal gas law when we hold certain variables in the ideal gas law constant. So again, it's important to remember that because R is a constant, the ideal gas law can be used to compare changing conditions for a sample of a gas as follows. So recognize the relationship that exists between those four variables, and because it's equal to a constant, anything that we change about those variables, the other variables are going to adjust in such a way so that the value is equal to the R value or constant value that we had under those original conditions. So if you wanted, you could use this combined gas law for every single problem that we're going to do. But recognize that many times we're only focused on one or two variables while holding the others constant. And so we can use our amazing math skills to derive more simplistic gas laws by holding two of the variables constant. So the first law that you want to be comfortable with is Boyle's law. And this law states that the pressure of a fixed amount of gas varies inversely with the volume at constant temperature. Now, we can describe Boyle's law to compare changing conditions as follows. We're going to start with our combined gas law, all of those variables included, but Boyle's law is focusing on just the pressure and the volume. So let's plug in some simple numbers to help us think about Boyle's law. My initial conditions: pressure of 1 atmosphere, volume 1 liter, number of moles 1 mole, temperature 1 Kelvin. Just go with it. I know that's really cold. Keeps the math simple. Our focus in Boyle's law is on the pressure and the volume. If we keep these other two variables constant, if we're keeping those variables constant, when we're solving for this volume, in this case, the number of moles and temperature will essentially drop out of the equation because they're held constant. Boom. That simplifies the math. So if I were to say double my pressure from my initial pressure, what must happen to my volume? Bet you can do this one without a calculator. We're going to decrease the volume to 0.5 liters. Inverse relationship between pressure and volume. That is the relationship that Boyle's law describes. And it's a simplified version of our combined gas law when we keep the number of moles and temperature constant. All right, now it's important that you can understand Boyle's law in graphical format as well. The graph that you see on your screen and in your notes describes that inverse relationship that exists between pressure and volume. As my pressure increases, the volume decreases. Inverse relationship. With Boyle's law, we're looking at volume and pressure. Notice that as the volume decreases, check out that pressure. It is increasing. Can you handle it? Increasing the volume decreases that pressure. Pretty magical relationship that exists between volume and pressure. Boyle's law. Charles's law. Another simplification of the combined gas law. This states that the volume of a fixed amount of gas varies directly with the Kelvin temperature at constant pressure. So now our focus is on volume and temperature. Again, start with the combined gas law. Now let's think about the relationship between volume and temperature when we hold the pressure and number of moles constant. Again, mathematically, because the pressure and number of moles is held constant, they are essentially eliminated from the equation. To simplify the math, If I've doubled my Kelvin temperature, what must have happened to my volume? You guessed it, it must have doubled as well. A direct relationship. As that temperature variable increased, so did the volume. Simplified, Charles's law looks like the following. Kind of like the combined gas law, just without pressure and number of moles. Once again, you should be comfortable with interpreting and describing Charles's law in graphical format. Notice how this relationship differs from Boyle's law. Take a look at that graph. We've got a nice direct relationship between temperature and volume. As one of those variables increases, the other increases as well. Important to note, when you're working with the gas laws involving temperature, your temperature has to be on the Kelvin scale. And that's to avoid some impossible negative things, like you can't have a negative volume. So make sure your temperatures are always in the Kelvin scale. All right, now let's take a look at this simulation in terms of Charles's law, or the relationship that exists between temperature and volume. As I increase the temperature, notice what happens to my volume. My volume increases as well. Direct relationship. If I cool things down, if I decrease the temperature, notice that my volume decreases as well. Oh, Chucky's law, so magical. All right, moving right along. As we get to Gay-Lussac's law, this law states that the pressure of a fixed amount of gas varies directly with the Kelvin temperature at constant volume. Now we can use Gay-Lussac's law to compare changing conditions as follows. Once again, we're going to start with the combined gas law, but this time our focus is going to be on the pressure and temperature variables. We're going to hold the number of moles and the volume constant. Once again, our math will simplify. And again, think about the relationship that exists between pressure and temperature. It's a direct relationship. If I were to say double the Kelvin temperature, what must happen to the pressure of that gas? It would have to double as well. And again, this can be simplified from the combined gas law to the expression that you see on your screen. P1 over T1 equals P2 over T2. Now, once again, you want to be comfortable expressing this gas law in graphical format. A direct relationship, you're going to need a nice linear relationship between pressure and the Kelvin temperature. Once again, because temperature is involved in Gay-Lussac's law, you want to make sure that it's on the Kelvin scale. Now let's take a look at Gay-Lussac's law, the relationship between pressure and temperature. Increasing the temperature, heat 'em up, speed 'em up. Woo, check out that pressure. It's getting insane in there. Direct relationship. Notice if I cool things down, decrease the temperature, notice that my pressure decreases as well. Gay-Lussac's law. Which brings us finally to Avogadro's law. This is a simplified gas law that focuses on the volume and the number of moles of a gas. Here, we're keeping temperature and pressure constant. Use Avogadro's law to compare changing conditions by starting with your combined gas law. Again, I'm going to plug in some simple numbers here just to make the math very easy to understand. Recognize that we're keeping the pressure and the temperature constant, so our focus is going to be on the volume and number of moles. Notice once again the direct relationship that exists between volume and number of moles of a gas. If I were to say double the number of moles of gas, in order to keep temperature and pressure constant, my volume would have to double as well. Avogadro's law, relating volume and number of moles of a gas. Just like the others, you want to be comfortable looking at Avogadro's law in graphical format. Recognize that this is going to be a direct relationship, so you'll get a nice linear graph that exists between volume and number of moles. All right, finally, let's take a look at Avogadro's law. This relates the volume and the number of moles of my gas. If I increase my number of moles of gas, my volume's going to increase as well, in order to keep those other variables constant. All right, that does it for this vid. Be sure to check out some of those guided practice problems to get comfortable with the calculations that you're going to have to do when it comes to the gas laws. Have a fantastic day.